This is Bob Capetta from the University of Illinois at Chicago, and this is yet another lesson on power series. So the goal is to use a power series to determine the integral of 12 over 3 plus x dx, and then examining that power series, find the interval of convergence. So we're starting with 12 over 3 plus x. We want to write it in the form a over 1 minus r. I need to turn that 3 into a 1, so I'll divide the top by 3 and divide the bottom by 3. 12 divided by 3 becomes 4. 3 over 3 is 1, plus x over 3 on the denominator. We want to match this to a geometric series. And we know that if the common ratio is between negative 1 and 1, the geometric series will converge to a naught over 1 minus r. So we're assuming this is in the form of a naught over 1 minus r. If that's the case, our a naught is 4 and our r is negative x over 3, because 1 minus negative x over 3 is equivalent to 1 plus x over 3. So we have our first term and we have our common ratio. Now our goal is to find the integral of this function, but as long as we're here, let's talk about the interval of convergence for 12 over 3 plus x. We know the common ratio must be between negative 1 and 1. So negative 1 is less than the common ratio of negative x over 3, which is less than 1. Multiplying both sides by 3, we get negative 3 is less than negative x is less than positive 3. And then multiplying both sides by negative 1, of course, you have to switch the signs. If you do that, we get 3 is greater than x is greater than negative 3. Or the interval of convergence for 12 over 3 plus x will be the values between negative 3 and 3. No need to check the endpoints because all we used here was the geometric series test. In a geometric series, if the common ratio equals 1, the series will diverge. So here is our situation. We have an initial term of 4 and a common ratio of negative x over 3. So 4 plus 4 times negative x over 3, which of course is minus 4 times x over 3, plus 4 times negative x over 3 quantity squared. Well, negative x over 3 squared is positive x over 3. And you get the idea. When we have a common ratio with a negative sign, we typically alternate plus minus plus minus plus minus. So we've expressed 12 over 3 plus x as a geometric series, as an infinite series, as a power series. We want to take the integral of this, so we've got to integrate each piece. So what will the integral of each piece be? Well, maybe before we do that, let's do a little bit of algebra here to make this manageable. So I will rewrite x over 3 squared as x squared over 3 squared and move the 3 squared with the 4. Rewrite x over 3 cubed as x cubed over 3 cubed, move the 3 cubed with the 4, etc. So now if I want to integrate each piece, the integral of 4 is 4x, the integral of x is x squared over 2, multiplied here by that 4/3. The integral of x squared is x cubed over 3, multiplied by 4 over 3 squared. Integral of x cubed is x to the 4th over 4, multiplied by 4 over 3 cubed, again with the alternating signs as well. So let's see what that looks like. We take the integral of each one of those pieces, and we can see where we are. Now, resist the temptation to multiply the denominators. Our goal is to look for a pattern. Can we see a pattern in these numbers? We put the plus c first. If we're integrating something, of course, we have to have a plus c somewhere, so I put it first. The integral of 4 is 4x. Integral of x, x squared over 2, etc. So you'll notice that x squared over 2, x cubed over 3, x to the 4th over 4. This is what? This is maybe when k is 2, maybe when k is 3, maybe when k is 4. So we can see x to the k over k. Every term has a 4 in it, but then the 3, you'll notice, does not have the same exponent as the x. 3 has an exponent of 2, x has an exponent of 3. Here, 3 has an exponent of 3, x has an exponent of 4. So it appears as if the exponent of 3 is 1 less than the exponent of x. Also, you will notice that we have a sign change. Positive, negative, positive, negative, positive, negative. How do we make sense of that? Well, if we're going to let this x be 1, you'll notice the sign is positive when x is 1, when the exponent of x is 1. So when k is 1, the exponent is positive. Well, negative 1 to the k is not going to work because negative 1 to the 1 is negative. If we want the sign to be positive when the exponents are negative, we're going to need to use a k plus 1 for our exponent on negative 1. So now that we've talked through that, see if you can decide what that pattern is going to be. Can you identify that? If this is going to be the piece where k is 1, this is the piece where k is 2, this is the piece where k is 3, this is the piece where k is 4, this is the piece where k is 5. Can you see that pattern? Well, here it is. Negative 1 to the k plus 1, as we mentioned. There's the 4. X to the k over k that we mentioned. And in the denominator, we have 3 with an exponent that's 1 less than the exponent on x. 3 to the k minus 1. So can we find the interval of convergence for this function, or this family of functions? So we've got the absolute value of a sub k is 4x to the k over 3 to the k minus 1 times k. By taking the absolute value, we lose the sign flasher. The absolute value of negative 1 to the k plus 1 is really the absolute value of either negative 1 or 1, which of course is 1. Now, the absolute value of a sub k plus 1, replace all the k's with k plus 1. So we get 4x to the k plus 1, 3 to the k plus 1 minus 1, and then k plus 1. And of course, 3 to the k plus 1 minus 1 is just 3 to the k. And using the ratio test, we need to take the limit as k goes to infinity of the absolute value of a sub k plus 1, this, divided by the absolute value of a sub k, this. Again, 4x to the k plus 1 over 3 to the k times k plus 1 divided by 4x to the k over 3 to the k minus 1 times k. If we're going to divide those two fractions, we should invert and multiply. Change that to multiplication, flip the second fraction, and we get this. Now what does this reduce to? 4 over 4, the 4 is going to cancel. X to the k plus 1 over x to the k, that's x to the k plus 1 minus k, that's just x to the first power. 3 to the k minus 1 over 3 to the k, there is one more 3 downstairs, so that will indeed give us a 3 downstairs. And then k over k plus 1 will maintain itself. And of course, this should be absolute values. So we're taking the limit as k goes to infinity of the absolute value of this. When we reduce that fraction again, x to the k plus 1 over x to the k is x. 3 to the k minus 1 over 3 to the k is 3. The 4's cancel, and then k over k plus 1. So at this point, we can pull out the x over 3. K is changing. Limit as k goes to infinity. X is not changing here. So the absolute value of x minus x over 3 can come out in front of the limit. So we get absolute x over 3 times the limit as k goes to infinity of k over k plus 1. And of course that limit is 1. So the result is simply the absolute value of x over 3. And what do we know? For the ratio test, we need that limit to be less than 1. So we need the absolute value of x over 3 to be less than 1. We need negative 1 to be less than x over 3, which is in turn less than 1. And then multiplying by 3, we get negative 3 is less than x is less than 3. But we use the ratio test here, and the ratio test is inconclusive if the limit is 1. So what do we have to do? We have to check the endpoints. So we'll go back to this function and we'll see, does it converge at 3? Does it converge at negative 3? So I'm going to define this function g of x, and instead of plus c, I'm going to put plus 0 there to get a feel for how this operates, to determine our interval of convergence. And I want to apply the function g to 3 and to negative 3 to see if it converges. So g of 3, which is essentially defined as that integral with the constant of 0. Replacing x with 3, I get the sum as k goes from 1 to infinity, negative 1 to the k plus 1, 4 times 3 to the k over 3 to the k minus 1 times k. Let's think about this for a minute. The only thing we're going to lose is 3 to the k over 3 to the k minus 1. And that will divide out, leaving a 3 upstairs. So the sign flasher, negative 1 to the k plus 1 is still there. 4 times 3 is 12. 12 over k. So 4 times 3 is 12. 12 over k decreases to 0. And this is an alternating series. So what does that tell us? We know that the series must converge by the alternating series test. So 3 is indeed included in our interval of convergence. So the question next is negative 3 included in our interval of convergence? So we're going to replace the x with negative 3 and see how that behaves. So g of negative 3 is the sum as k goes from 1 to infinity, negative 1 to the k plus 1, 4 times negative 3 to the k over 3 to the k minus 1 times k. Well, I think I want to rewrite negative 3 to the k as negative 1 to the k times 3 to the k. That will enable me to divide out the 3's, and we can think about how the negative 1's are going to behave. So 3 to the k over 3 to the k minus 1. There is one more 3 upstairs. So again, that will result in a 3 upstairs. But now how about the negative 1's? Negative 1 to the k plus 1 times negative 1 to the k. Bases are the same, add the exponents. Negative 1 to the k plus 1 plus k, or negative 1 to the 2k plus 1. So indeed, negative 1 to the 2k plus 1, 4 times 3 here will be 12 over k. Is this an alternating series? If it alternates, it will converge, but you will see it isn't. Because what is 2k plus 1? If k is 1, 2 times 1 plus 1 is 3. If k is 2, 2 times 2 is 4, plus 1 is 5. If k is 3, 2 times 3 is 6, plus 1 is 7. 2k plus 1 is always an odd number. Negative 1 to an odd number, negative 1 to the first, negative 1 to the third, and negative 1 to the fifth, is always negative 1. So we get negative 1 times 4 times 3 over k. This is no longer alternating. This is the sum of negative 12 over k, which is a multiple of the harmonic series. So we pull out that negative 12, and I get g of negative 3 is negative 12 times the sum as k goes from 1 to infinity of 1 over k. We know that diverges. We know the harmonic series diverges. So g of negative 3 does not exist. So negative 3 is not included in the interval of convergence, but 3 was. So then what is our interval of convergence? Not including negative 3, but including 3. So you'll see x is greater than negative 3, but less than or equal to positive 3, a half-open interval written this way. And that will conclude this lesson.